Okay, Unit 6 was all about rational functions, and remember the definition of a rational function is any function that is the ratio of two polynomials. So sometimes we've written it like nx over dx, where both of these guys are polynomials, except d of x can't be 0. The simple polynomial equals 0 because you can't divide by 0. But other than that, if you have an expression that can be written as two polynomials, you'll have a rational function. And notice how the word ratio shows up here. A ratio is like something's in a ratio of 3 to 1. You can write it like that. That's why the name shows up there. Rational numbers are any number that can be written as the ratio of two integers. You know, like 9 over 7 is a rational number. So just trying to again show why this adjective rational shows up in this idea of division. So problem 19 here is all about deciding whether these are rational functions. This amounts to really determining whether the numerator and denominator are both polynomials. If you're not sure how to classify a polynomial, you can go back to Unit 5 and watch some of those videos. But essentially, that's what we're going to do here. That's a polynomial, that's a polynomial, you're dividing them, that's a rational function. This one here, this is written in factored form, so that doesn't change that it's actually a polynomial, so it doesn't look, again, factored form of polynomials is something we talked about in the prior unit, Unit 5. This is a polynomial, so the two polynomials are being divided. Yes, rational function. Here, this box here, that's definitely a polynomial. This one, though, if I wrote it with its fractional exponent form, x to the 1/2, that doesn't meet the definition of a polynomial. So this one is not. Here, constants are polynomials. You can refer back to Unit 5 videos if that's not clear. X is a polynomial, and so, yes, this is a rational function. This is also a rational function. I know it seems odd that it's a constant, but I guess it technically does meet the definition. So this is just the function y equals 3/4, so if you graphed it this way. But this could be written as 3x to the 0 over 4x to the 0. And so therefore this technically meets the definition of a rational function. Here, this one throws off a lot of people because they see the square root of 2 here, and somehow that makes them think it's not a rational function. Again, determining whether something's a polynomial, that every term has to have a coefficient, a variable, and a power. The coefficient can be anything. It can be, like this would be a polynomial. Pi x cubed squared plus ex plus square root of 2. The fact that these coefficients are these weird irrational numbers doesn't make it not a polynomial, right? All we have to do is look at those variables, x squared, x, and this would be x to the 0. So this square root of 2 is not part of the exponent or anything, so this is a polynomial, this is a polynomial. So the answer here is also yes. So the only one that's not is this one. Since we work a lot with reciprocals in this unit and dividing fractions, this is more of a just making sure you understand how to clear fractions and simplify fractions of fractions. If you notice this is just 1 over a fraction, so if you recognize that as taking the reciprocal, you should see right away that this will be 11/21. But really that's not the goal here. The goal here is to actually do some math on this to see why this would be true. So there's two ways you can think about this. The one I like is where you're trying to clear denominators from fractions. So we see that there's an 11 in this denominator, so we can strategically choose what we've called the funny form of 1 to get rid of that. So if I multiply the top and bottom here by 11 over 11, I can do that because that thing equals 1, and by multiplying by 1 doesn't change anything. And so now I can multiply numerators and denominators when I do this. So I have 1 times 11 on the top. Have 21/11 times 11 on the bottom. This number times this number. And that just simplifies to 11. And then 21 over 11 times 11, those 11s will cancel. Gets you to 11/21. The other thing to remember, you could say, is when you divide by a fraction, that's the same thing as multiplying by a reciprocal. So 1 divided by 21/11 equals 1 times 11/21. And so that equals 11/21. Yeah, that's the way you might have remembered dividing by fractions, but trust me, this way of clearing denominators is a much more intuitive and more widely useful idea to apply here. So for C over here, we see that we have a denominator of 2 here, and there's no denominator up here. So to clear the fraction, I can strategically choose 2 over 2. Again, that's 1. And then I can go ahead and 40 times 2 is 80. 1/2 times 2 on the bottom here, let's list 1/2 times that 2 equals 80 over 1. And that equals 80. Here, this idea of clearing fractions when we have multiple ones is to multiply by the least common multiple of those numerators. So if I want to, basically I want to find some number that's going to get rid of that 5 and that 40 at the same time. So the least common multiple of 5 and 40, LCM. So a number that both 5 and 40 goes into. You don't have to pick the least one, but that's usually the best choice here. Well, actually 40 will work here because 5 goes into 40, 40 goes into 40. So if I choose 40 over 40 for this one, I'll have negative 1/5 times 40 over 7/40 times 40. And then that 5 will cancel here, because 40 over 5 is the same as 8 over 1, that's negative 8. And the 40 over there gives us negative 8/7. Here, this is just another reciprocal one, 1 over 1 over a million. This is just trying to tee up the idea that if you take the reciprocal of a tiny number, like in this 1/1,000,000th is a really small number. If I take its reciprocal, I'm going to get a big number, and let's convince ourselves why that is. If I multiply this by a million over a million, again, I chose that because that's the denominator. The goal here is to clear denominators. I get a million, over 1/1,000,000th over times a million is just 1, or 1,000,000. So we have this idea that, and we'll talk about this shortly, that a huge number, 1 over a tiny number is a huge number, and that's really what happened here. This one's huge, and that one is tiny. 21, you might remember this from the review packet when we did this unit. It's just trying to show mathematically why flipping actually works. Reciprocal is defined as this function here, right? A lot of this unit's about the reciprocal function. F of x, take an input and take 1 over it. That's reciprocation. So, but a lot of people remember reciprocal as just flipping. Like here it says takes 2/5 and flip it. So the question is, are these two things actually the same thing? Is the shortcut that you've learned actually have meaning in the context of what the definition of reciprocal actually is, which is 1 over a number. So if we take, that's the idea here, is take some generic number a over b, put it into the reciprocal function. So I'll do that here, f of a over b. And the reciprocal function is 1 over whatever input I put in. So that's going to go there. Now I have this expression. This should now look familiar since the review problem 20 was simplifying a lot of this. Things of this type, but just with numbers. Goal here, clear denominators. Well, I see b in the denominator there, so if I strategically choose b over b as my form of 1, I'll get 1 times b in the numerator here, a over b times b in the denominator. Well, those b's cancel, and that equals b over a. So now we can see kind of why flipping works here. If I put in a fraction into this reciprocal function, the output is the flipped version of that. But it's important to understand why that works here in the context of the definition